Are you ready for cognitive design computing? That's what we'll talk about today. Cognitive design computing. What might that be? In case you're wondering what these flowers here are in front of you, these red flowers, last Friday we had the whole leadership of the SBB, the Swiss Railway Company, and the board of ETH here in this room. They were sitting in your place, and here we were showing what the future of the transportation and mobility will be in Switzerland. So it was quite an intensive meeting all Friday afternoon. We are quite advanced now. We are today on responsive cities and this cognitive design computing. I hope, hello, you will understand what it is. And next week, I already want to announce this at 2 p.m., from 2 to 6 p.m. We have the presentation of selected number of exercises from your course, from the programming course, and from the simulation course. Story so far, you can see as it evolves. And today, cognitive design computing. Last week, urban governance, specific to each city and determines its development. And now today we have the technical means to also determine or co-determine the development of the cities. That's the content. We'll start with a short definition, and then we have a real professor here, a professor that you already know, Professor Dr. Reinhard König. He will give you his view of the cognitive design computing. Then we have our eternal example with the Cooler Karma Singapore for your exercise and for this field as well. I hope we'll make it, but who knows? And finally, some conclusions. Here's a short definition. What is this cognitive design computing and why is it important? It extends the application of IT into data and information-rich dynamic situations. So it takes it out of the normal environment, sitting in front of your desktop and just trying to reason about things very structured way. It is supposed to deal with very complex situations that change. It is supposed to answer day-to-day questions. And therefore, the first applications that Reinhard König will also show are in the chess area or in the Jeopardy games area. It began as a concept already in the 1950s, and it was somehow related to the development of artificial intelligence. Artificial intelligence was born before all of you, but it is an area that was sleeping for a while and is now gaining more attention again because of the new capabilities of machines and software. So it's related to artificial intelligence, and it's supposed to also include the cognitive capabilities of a person, of a human, and combine it with computational means. It's easier said than done, as we will see. Architecture, from the very beginning, provided a very good application area, because in architecture, you have all these different demands on the design process, on the final product, and no computer program at this time, in the 50s, the 60s, the 70s, or 80s, up to today, could really deal with this directly. So therefore, it's a hard problem to design, to use cognitive computing in architecture, and we find a lot of applications in this area. However, because architects are not organized in big organizations, basically everybody works for herself or himself or in small teams, research, real deep research, heavily funded research in this area, cognitive design computing, did not occur, and it is only recently with faster machines and better programs that we can go to this point again. So architecture is a good application area, and urban design is an even better application area because the amount of structured information is relatively little, and the amount of unstructured dynamic information, as you saw, all these big data in the city, is really strong. Cognitive design computing will then be the combination of architecture and urban design cognitive computing, and we hope this will be a great tool for the future. We already working on the preparation of this tool and this method definitely in our Singapore project again. It's called Big Data Informed Urban Design. And in this Big Data Informed Urban Design, we have a lot of individual programs and people working on. But you see one area here. This is called the work stream number 2, Cognitive Urban Design Computing. This is the area which focuses entirely on that. And in this field, Professor Koenig will be the co-principal investigator, and we're building up a research group now in Singapore to work on this. In the end, to give you a picture, maybe to understand it better, it would be something like that now in architecture. Here you see humans standing there in front of the machine. This is one of the robots that you can see now in more advanced version over in the robotic lab of architecture. But the robot is really dumb at this moment. It has only the instructions that it got from the programmer, and it will execute these instructions somehow. Cognitive design computing would be slightly different. Now this, for example, is the Minister of the Environment in Singapore, and he would talk to this machine, and he would tell this machine, this supposedly a high-rise is not high enough, or something like this, or not broad enough, or it's too thin, or too broad, or whatever. And accordingly, then the machine could start to react, and not only in a simple way, but could take also the comments from another person. This one here, for example, behind the hand of the person. Has somebody recognized this person? This is our Swiss Minister of Labor today. There's Mr. Berset is there. Or this one, you know this person here? No? This is the chief executive of our ETH domain board. So all of them, of course, have things to say how the future architecture and building industry should develop. And in the future, maybe we can directly talk to this machine. That machine will also talk back to us and give us the limitation it faces. As a very simple example. Now let's go a bit deeper and introduce Professor Reinhard Koenig. Reinhard.
Thank you.
And all of you who take the urban design course, of course, know him. For the others, he is at the same time here and at the Bauhaus University in Weimar. He was at the Technical University in Munich before, also last year, as a professor. And now he will talk to you about his view on cognitive design computing.
Yeah, thanks for the introduction and welcome. So I will try to show you or to introduce you first of all to the more specific parts of how we can apply this technology, this technique, this approach of cognitive computing to design. And I will show you first examples how this could look like, and then we can also speak about possible paths to the future, how this technology should evolve. So first of all, what Professor Schmidt already mentioned, in 1997, there was the computer program Deep Blue. Has anyone heard about it? At least when I was young, this was a very important event when the first time a computer beats the chess champion Kasparov at this time. So this was the first moment when a computer was able to do something that was linked with intelligence. Playing chess was meant to be a difficult problem. And in this time, a computer was able to win this game. Of course, this was a very limited world. So probably all of you know chess. So there is a set of rules, and you have a board, and that's the world that the computer needs to understand. So it's not comparable, for example, to design, because design is an open problem. You cannot define it as a game like chess. And now in 2011, this was the next step in the evolution of these computers and the computer programs. Again, IBM, who developed this Deep Blue, they developed a system called Watson. And this time it was able to win in a game called Jeopardy against the Jeopardy champions. And the big difference between chess and Jeopardy is in this game, the players are asked open questions. So the difficult thing for a computer is to understand the context of a question. So maybe you already have experiences with your computer tools. Often the answers are difficult because they don't understand the context. If you ask for some help, for some problem with your computer, it's often very limited. This system was able to understand very complex questions and especially the context of the question. So often to solve a problem is a relatively simple task. To understand the context of a problem, it's often the most complex and complicated problem. So this was in 2011. And now the question is, how can we apply it for creativity, for creative tasks like design or planning, what you are studying, what we are interested in, to apply or to find possibilities to take this away from playing games into design. So IBM itself, they applied it to creating or to develop new cooking recipes. Like here, you see there is this apple pie model where they mix ingredients and to create new food or new models, for example, for an apple pie. So that's, of course, cooking is also a creative task. If you've cooked something by your own, you know to mix ingredients is not that straightforward. So that's a creative application, how they apply it. What we want to do, what we try to do is to apply it in design. So the idea in the end is that we have something like an artificial intelligence that helps us to solve design tasks, to design something that is more or less a co-designer. If you work with some other human designers, so you are a team, you tell each other your ideas, and you develop the project. So the idea is that the computer can take over this role and help you to work on a problem. And before we look into some examples, let me introduce some of the most important aspects of cognitive computing. So as already mentioned, we are now able to solve problems of a new class compared to chess, for example. So this means that these are open problems. And they are now computable and they address complex situations. So they are not clearly defined. So they are uncertainty in the context of these problems or under the conditions. It's not clear what you handle with, what you deal with. And often during a project, for example, in urban planning, your information that you deal with, they change or you collect more information, you make another analysis, you get some information from another stakeholder. So the context is changing. And sometimes it's also conflicting, or usually not sometimes, always your design task, you have conflicting requirements. And your own goals may also evolve over the project, over the time of your own design. If you draw something, if you make sketches, usually you learn about the problem, you learn about the task, and you evolve your goals. And these tools, so now they are not only able to analyze your designs, to tell you how good it is, or what's the performance. The idea is that they create designs, that they are somehow as smart as yourself, that they can produce solutions. This doesn't mean that these systems work like a chess game where you can make a right or a wrong move that leads to win the game or to lose the game. These systems, they try to help you somehow. They try to find out what you want to do, and they want to support you in a way that they offer you good or the best solutions, but it's never the case that it's right or wrong. So this is also what should be expressed by this slide. Often computers try to find the best solution, what should be here. So if you are on the top of a mountain, that's the place where you reached more or less the best design or the best solution for something. What these systems try to do, they try to show you good paths. They try to show you directions where you should go with your design to find some better solutions. So now some of you have seen this already in the other lecture. These are examples how such systems could look like. So here you have some requirements for floor plans. You write them down in a boring table, and you have the sizes and the minimum length for rooms, for example. So you start with telling your computer what you want to get. And then you receive a geometric solution for these requirements. And that's now the special thing with design. So we are not looking for rules in a game. We are not looking for text answers, and we are looking for geometric solutions. And this makes it special, cognitive computing in design, that you need a geometric solution that, with which you can work with. And as you can see here, you as a designer, that's not a system that creates a solution and says, okay, that's it, take it or leave it. You can interact with the system. So you can include your capabilities, your thoughts into it by manipulating the geometry or changing the requirements. So that's the very, very important thing why it's called cognitive computing, because it tries to include your cognition. There's always a part that you know better than the computer. So you need to be able to integrate your knowledge in a system. But some parts can be solved better by the system. So ideally, you and the computer form a team that can help each other. That's another example. You have seen floor plans. Now you see how it could be applied for urban planning problems. That's an area in Singapore where we tested the approach to create some urban fabric like this, where you have a street network, and you start with a random setup, and then you tell the computer some requirements for this network, and then the system try to explore the possible, or the space of possible solutions together with you. So in the next step, you will see in this window, there will be some street networks, and they all fulfill more or less the requirements that you can ask the system beginning, and then it's up to you to select something or to adapt it to the problem. And then you can test it, so that's then up to you what you think fits best and how you need to steer, how to lead the program to develop a better solution. In the end, you will find solutions like this that you can develop step by step by integrating many simulations. So in the background, you see here a simulation of view fields, what you can see at a certain area. So this can be included. So you can include everything that you can measure, that can test how good your design is, that the computer can help you to measure things that are usually very boring for you to do. So this is then taken over by the system. Okay, I will skip the rest of this movie. That's a project where we where we apply these techniques at the moment. That's a project in Cape Town, an area with these shacks. And the people there, they are involved in the process. So they are asked in a workshop how they want to upgrade their shack. So now they have a one-story shack. And the plan is to have here two-story shacks. And they can tell in a workshop the planners or the system how much money they have, how many square meters they want to get, and then we feed everything, also the neighborhood relations with whom they want to live together in a cluster, like these clusters here. And then the system creates a solution. And again, you can select and you can manipulate these solutions as a planner together with the people in these workshop setups. And in the end, you see here these guys, they're really building these buildings for themselves. So they now upgrade this area. That's a project together with the Urban Think Tank, the Urban Planning, Urban Design Chair at ETH. So they help the people there. They do these workshops, and we develop the technology to support the planners. These are tools, so that's probably the future. These cognitive computing systems, they don't want to stay in the laptops. They also move to the world of the mobile world, like your cell phone. And especially, you don't need to install them. They can compute somewhere in the cloud, and you have these web interfaces that's developed by a colleague of us, Artem Shirkin, here at the chair, or Patrick Janssen, a colleague in Singapore. So there are many approaches to develop interfaces to work with these systems, and they won't be these static systems that you know at the moment, like CAD systems. They are much more flexible. And last but not least, you also need these large screens to show various properties of designs, to evaluate them from many perspectives with many views. So that's how we apply it in workshops. That's the scenario in Singapore, this video wall and the screens where we can collaborate also over distances and in complex situations. So this was the story or first ideas, insights into cognitive computing for design. So now Professor Schmidt will switch to another topic, Cooler Karma Singapore, another aspect where we try to integrate this cognitive computing for design in another design project.
Thank you very much. So, maybe first there might be one question to you. Somebody has a question now? Is it a better picture? Yes, please.
Yeah, I thought your presentation was really interesting, but I wondered, because this school has a bit two positions, and one is very critical with this way of going with measurements, and that's how you create design. It's more cultural or historical. So I was wondering maybe what are the resistances you hear the most when you present these projects?
Yeah, I mean, of course, often architects, first of all, they are afraid that these systems more or less may take over their jobs, their tasks. My answer is always that if you think about mathematics and computers, when computers were developed, they don't take over the job of the mathematicians. They bring it to another level. So now mathematicians can do more complicated, more complex things. They can concentrate on the real important aspects of math. So that's the way I would consider what will happen to your future, to our future. As planners, we can concentrate on higher level problems, on different things, instead of taking care that the traffic can, or that the cars have enough space to drive around. So this is solved. These easy things are solved by the computer. But there are aspects that cannot be solved by the computer, and these are the things where your cognition is important. So everything that's not as easy, that you cannot formalize, that's up to you. And you control the system, because the system don't know what's right or wrong, what's the idea of a plan, of a project. This is up to you. But I think these are the core competences of planners, of designers. And this will be more important, and the technical things may be automatized, as everything in our world. And I think another aspect, sometimes people say you cannot measure that many things, but what we try to do is we try to prove that you can measure many, many things. Also aesthetical aspects, you can also measure indirectly what people think is a good design, a bad design. In the end, also this big data approach is that it's able to find out a lot of things that we cannot understand how it works, but it can solve these problems. It can find out something out of data. But that's a long story.
It's a long story, but it's a good story, and it brings us right to the point of the discussion. I think it's a very necessary discussion, always. Because there's the two sides. They are not really sides. They're just different positions in terms of thinking. If we apply some of the dynamics of learning to this process, then you will see that even the people who are critical today, they are much more advanced than, let's say, the people who were critical 15, 20 years ago. And so I think we all move together in this direction. You're right in the situation that you have learned in this course with today, with this cognitive design computing. This is the one, and the other one, the citizen design science. You have learned about two expressions that you will not be able to find on the internet yet. with the exception of where they are listed in this course. Maybe 2 or 3 more are popping up by now. But it's really new directions, new combinations. And yes, so we welcome this discussion with people who think this is not possible or not good or not achievable. So that's what we're looking forward to. Do you have another question? Yes.
I have a question. The programs that you show, are they?
Wait. Sorry.
Those programs of like layout planning and urban planning, are they using like their own systems, I don't know, like through algorithms like Grasshopper would process, or are they like based on like cognitive neuroscience, like design process, like Simon and Newell's studies, like they tried to do once?
So what you have seen, that's developed in the context of research projects. So these are more or less prototypes of software systems to test for us how this could look like. It has nothing to do with neuroscience. We try to couple statistical models and optimization technology and all these simulations, these urban simulations or other things. And in the next step, we try to provide them for the students, for you, in a way that it can be used, for example, as Grasshopper components, that you can use it and that you can play around with it, and to develop your own projects. But that's then a lot of work to create a good user interface or to ensure that it works in all conditions. That's usually not our job because we are interested in the research, but we try to do this to offer it to all of you to play around with it.
I mean, does the computer try to process like designers do, like trying solutions and then testing if it's working or not, and then like lateral thinking, putting new input, learning something and like going again?
I mean, what we are working on at the moment is that we give some designers, some students, some tasks, some design tasks that you should solve by using an online system, and that the computer can observe you while you solve the problem. And if many designers have solved the problem, the computer tries to learn what strategies you have applied to solve this problem and to reproduce these certain strategies to solve other design problems. So that's the ongoing research at the moment, that we really try to grab your knowledge and to put it into some artificial system.
Okay, you say knowledge, but I can say that if the computer is like observing how people perform, it's more based in like performative solutions rather than like using knowledge like cultural knowledge, like urban tissue knowledge, all this knowledge that we have, and that's why we produce things. Like, is it based on the how or in the why?
I would say both, but you cannot explicitly see the results. So these models that try to learn something, they have their internal representation of knowledge. You cannot find out what they have learned. You can just test if they have learned something that makes sense if you apply it once again. But it's a very abstract representation. And if it's cultural knowledge or performative knowledge, that's hard to differentiate because it's somehow everything that the computer can observe, but it doesn't distinguish it. Just take it. So it's hard to translate it back to our understanding. So these statistical models, they show you just some correlations, but they don't explain you why you see these correlations. It's just there. That's a bit difficult for us because we always expect some cause and effect things in our world, that if I drop something, it falls down. But in the computer world, that's not always observable. It just tells you if it was there, it will be there, not why. Nothing about gravity. You just will have these two positions.
You know, okay, I see it as a useful tool, but like to have it like side to a designer, like to improve the cognitive abilities. But like, I don't see like how can it be innovative or obviously not replacing the designer.
Yeah, of course, it's not the idea to replace the designer. It's the idea to empower you.
Thank you.
Okay, welcome.
Okay,
Next.
I would really love to have some real fight here between the big A or big D designers and the cognitive people will get to this point, I think, in the next months and years anyway, as this project progresses and the first results will come out. But I'm quite positive that it will have deep effects, also positive effects on our design capabilities, especially on complex design capabilities. It's not only architecture where this debate is going on. Some of you will know the Human Brain Project. Who knows the Human Brain Project? Who has heard about it? Yes, of course, everybody from western part of Switzerland will know about it very much for sure. See, this is so interesting. Just by being in a location closer to it, you know more about it, although it's something totally global, really. And in that project, exactly this discussion along the lines, what is a human brain really? What is it in the first place? What is it doing? How does it work? Is it fair? Is it possible to simulate this? Is it even meaningful to do that? Exactly this debate is happening there. So this is the debate on the hardware and the software of the process of cognition and the brain working, let alone applying it to another field. And all the fields that you know, engineering, architecture, design, and other fields will all suddenly be exposed to this question. What is it what we did in the past? Should we always keep doing it this way? Should we believe in this magic that it somehow happens? Does it happen through work, through learning? What is learning? So you will get into an endless circle of questions. We don't want to solve this question. We just want to offer a possibility, one possibility, an additional one. Okay, let's look at one thing that you could apply this for. And I want to go back to your exercise because, as you know, it's due on the 26th. And we really want to give you feedback as soon as you have handed it in. We'll go through it and give you feedback that you know about it. And then we also want to have about 4 or 5 of you to present that work next Monday in the overall presentation of all the work here. And it is really on this part 2 and part 3 where you focus on a particular stock and flow that you identify and try to improve that without negative side effects. This is very, very difficult. And I want to show you just one example where that is done in reality. Somebody can read this? What does it say?
It's Future City Lab.
Oh, thank God. That's good. Okay. So you also know this place, of course. This was before the big square here in Zurich was transformed into the Sechseleuten-Platz of today with all the hard surfaces. And of course, you know the Berg that is being burned at the end of the winter. And then what happens is it burns and eventually it explodes. And that's what people see. And this is one way that you can see. If you are an engineer or a specially trained electrical engineer or energy specialist, you see something else, I think. Anyone here from the masters, the systems masters? Yes, do you see that? You see that when you see something burning? I hope. Danielle also should see that. Only that, of course. Huh? But it means that something happens and that some energy is being transformed, and in the end you have heat emerging. And you have the same thing happening here. If you look at any city, especially those high-density cities, you have all kinds of energy transformation processes. And this is the cars, this is the refineries, this is the factories, this is the lighting. In all of these cases, there's a transformation of one form of energy into another one, and in the end, it ends up as heat. Same story. You should see this, and only this, maybe. And the architect sees something completely different, and the people who have studied system design, they love this because they see how beautiful this factory is done. And the ones who have done transportation design, like in the Bauingenieur here, they say, oh, this is so effective, all these cars going this way, the other that way, there's no mix-up. And so everybody can, or here, what a beautiful picture of these high-rises. Everybody sees something different in there. But in recent times, the heat coming from these events is getting very serious. And this is why I want to go back to this diagram that you have seen before and focus on that a little bit, on the meaning of that. This is the picture of Switzerland. How can you represent a whole country through its energy flows in terajoule in Switzerland? How can you do that? Is that even legal? Can you look at a country or the representation of energy stocks and flows in a country in this way? You could say this is complete nonsense because energy is flowing completely differently. This is too rough and this is not realistic and whatever. But it has to do with your exercise and it has to do with our whole course. Because you have entities that are somehow coming into the system. The whole thing is a system. Coming into the system, being transformed here in this area, and then turned into another form of energy, and then in the end, so-called being used. Of course, you cannot use it, but transformed into another form of energy. And the remarkable thing in Switzerland is that the energy mix, as it is today, is very diverse. So you have different sources of energy. You can see it. The wood, coal, waste. This is the brown at the top. Then you have the crude oil. This is the red. You have the petroleum, the orange. Natural gas, the yellow. Nuclear fuel, the green. Hydropower, the light blue. The new renewables, these are the very few at this time. This was in 2011. Not so many yet, much more now. Then electricity, this light blue one. And finally, district heat as another source that you can use here. And from this picture, you can see what happens with all this beautiful energy coming in at this point, being transformed and being turned into this where it's actually used and demanded. Are there any parallels that you can think of that you have in other areas? People who have studied something else. Any mechanical engineers here? No. Computer scientists? Not really. The energy people, of course, they can understand that quite well. But it all has to do with architecture, with cities, and the dynamics of cities. Architecture is mostly concerned with this here at the top, with this one, with the housing, and with this one, with the factories or the industry, and with this one here, the commercial part. Transportation and mobility that we had here in the form of SBB last week is concerned with this one here. And here we can see very, very different efficiencies. That's important also for architecture and other places. If you see that one here, that little blue line here, I always say only visible through the resolution of the screen, otherwise you wouldn't even see it. This is the electricity going into the public transportation in Switzerland, which is carrying a record number of people in a record distance every year, every day, compared to the very inefficient personal transportation in cars, burning lots of, as you can see here, petroleum, and in the end, basically going up in heat, and even worse, in noise, because you can connect to almost all of these parts here, also noise parts. So the bigger this thing here is, let's say so much for personal transportation, burning diesel and petrol, compared to the electricity here, which is much quieter and much less polluting at the end of the path. And here in Switzerland, because it comes, if you go back here, from this part, most of the electricity coming here from water, 60% of all electricity coming from water, and 40% from nuclear. So you could say this is a very clean kind of energy versus this one here, if you go back where this is coming from, all the way from imports, and imports being refined or used directly as a final product. But it's coming into the country as import, it's being transformed, and it's sitting in the country in the end as heat, as noise, as energy that is useful. Unfortunately, not so much energy of this is useful, and that's one of the problems that we have today. But if you look at the housing sector here in Switzerland, it's 27% of the total energy demand. If you look at the industry sector, it's only 19%. If you look at all the commercial sector, it's only 15%. And you can see the high degree of electricity going into each one of those. From that, if you say you want to reduce the heat or the noise in a country, it's pretty easy to see where you have to start. You should probably start here in transportation, then go to the housing, and then go to the industry, and then go to the commercial. Who is taking Jan Camelier's class on urban heat islands? Or who has taken Jan Camelier's class? So you know about the urban heat island effect, right? Okay, so here we have an urban heat island effect, which is caused by these energy inputs, of course. But it's based on an average temperature of maybe, do you know the average temperature in Switzerland? The mean temperature per year? You don't know? Hard to tell. But it's in the 14, maybe 13, 14 degrees. Here we come to another country in the tropics, Singapore. We have the average temperature of 27, by now 28, sometimes 29 degrees. And you can see per person 531,000 terajoule of energy demand in this country versus 852,000 terajoule in Switzerland. That means per person with more than 8 million inhabitants in Switzerland and 5 million inhabitants in Singapore, it's the same per person energy demand and consumption. But here you see a radically different view. This one here is the dominating factor. Anyone who knows why? The people from Singapore still here? Yes? So why? Can you imagine why this is so big?
Because we do oil refinery and we don't need heating for our houses. Yeah.
That's one big explanation. Yeah, much of this industry is actually oil refineries, so it emits not only a lot of heat, but also pollutants. And you say you never need to heat, of course, in Singapore. You need to cool the buildings, but the majority of the building stock in Singapore, all the Housing Development Board buildings, do not have air conditioning by default. They can be put in later. So you have a relatively low heating, no heating demand, relatively low cooling demand, mainly delivered by electricity and a little bit by natural gas directly and for the other energy sources like cooking and so on. But this is absolutely dominant. Then all the commercial part is relatively smaller also than in Switzerland, because again you don't have heating, only cooling, and lots of electricity going in, of course, and some for cooking and other gas needs. And you have the private transportation. Not surprising that you have less energy use in private transportation because the country is very small, and therefore you don't have all these long driving positions. You don't have this mountainous territory going up and down, and most of the people are quite smart and use quite efficient machines. So you can see a very different pictures in Singapore. But also here, all the transportation in Singapore like the mass rapid transportation, the subways, the S-Bahn, the trains, whatever you would call it here, are also delivered by a very small part of electricity, as you see here. But if you look where the electricity is coming from, you can see this one, and that means almost all of the electricity is made from natural gas. And by making from electricity from natural gas, you set free a huge amount of energy, again, of heat as a byproduct. So this is almost 100,000 terajoule that you just give out as heat. So you have very different pictures, and you have only 2 energy sources in Singapore, 2 primary energy sources. And if you go back to Switzerland, you see it's a very diversified energy picture. So in Singapore, of course, you would start with industry to reduce. And then you would go maybe to transportation, but then also look very quickly at this transformation losses or production of heat here in the natural gas. There you see, these are the big contributors to heat flux: industry, transportation, buildings, and the existing urban planning model. Because moving people back and forth, like in every country, with this you can control more or less the amount of transportation that you have in a country. And this is a design decision if you really want to do it right. And to make the picture even clearer, when you look at the size of Singapore, this is exactly the size of Lake Geneva. And then you imagine you would put, there you have the mean temperature of Lake Geneva area around it, 11 degrees. Then you would put about 80% of all Swiss energy onto this Lake Geneva, and then you can imagine what the heat island effect would do to this lake. So this is the size of Lake Geneva was Singapore maybe in 1980. By now it's more than 700 square kilometers, but it's still in the same vicinity. If you then would make a so-called Milchmädchenrechnung, we know that about the urban heat island effect in Singapore is about 5 to 6 degrees, depending where you go. So let's just make a simple assumption and relate it to the energy demand of Singapore, which is 531,000 terajoule per year. And then you could say, okay, if this is the terajoule and this is the heat island effect of 5.3 degree, then we could almost directly relate these, or we can try to relate directly those contributions from left to right. What is the mistake that is made here in terms of thinking?
You just directly divide it and put decimal points of what the industry transport buildings are. You didn't consider embodied energy or any of the other inputs that would lead to actually have a cost. I'm not sure if it's totally translatable to from terajoules into
Exactly. I mean, this is one mistake, and the other mistake is that, of course, just by having a city there, sitting there, which is different from the rest of the countryside, even if there would not be a single person or car or train in this city, there would still be some kind of heat island effect just by the morphology and the roughness generated by the city being there. So that would make about 2 degrees. That's a very rough estimate, but that's what the specialists say would be about 2 degrees. Anyway, even if you detract these 2 degrees from these numbers, then you could still come to some relation. And if you just look at the biggest contributors that we think exist, industry, because it's direct heat output, transportation, again, direct heat output through exhaust and radiation, and buildings, relatively little, and the electricity generator, this is definitely direct heat output. Then you would know what to do. The buildings, you could look at. The transportation would probably have more effect. And then, of course, the biggest one would be the industry. And what we are now studying in Singapore, and that would be an interesting combination, again, for your exercise at home. If you say, okay, let's just take out the cars, all the cars, what would happen? What do you think? Would it get cooler or hotter, or what would happen?
I think we would still have the infrastructure, the pavement, and that also affects the.
Yeah. But do you think it would be cooler without the cars, or not?
Probably, like without the emissions, yes.
Emissions and radiation directly from the cars. But this is most likely it would get cooler between 1 and 2 degrees alone through these 850,000 cars which are running around there. But this exactly is the subject of research now, because the interaction that you mentioned between the emission of the cars in terms of exhaust and radiation is counterbalanced by, let's say, the effect of the trees, which have some effect, but not the effect that most people think they have. But they do have some cooling effect, which now we can quantify. But the interaction between the car and the radiation of the car's engine onto the ground, onto the street, and then the re-radiation from the street into the environment is not known at the moment, not known exactly, and therefore this is a part of the research. So here you see those very hot cars, and they're literally very hot, running through the city. It's like a floor heating system for the whole city, which is quite nice in cold climates, but not in hot climates. And then, of course, the buildings, they interact with the cars, or the cars interact with the buildings, because the heat is rising up, it's affecting the cars. Also, the noise from the cars is rising up, and it's hitting on each apartment in the whole city, and it is very, very, very strong. So taking out the buildings, what would happen? Would it get cooler?
Yes.
Yes, yes, it would get cooler. As a matter of fact, it would get probably as cool as in the central part, at least as cool as in the central part of Singapore, which is still a jungle area and the reservoir area. Do you know how much cooler it is in the reservoir in like McRitchie Park than in the downtown area?
I don't know exactly, but it feels a bit like 2 to 3 degrees cooler. Plus there's a lake, like a pond there, so.
Yes, yes. So you're right. In the pond, where the big reservoirs are, where the rainwater is stored for use later, that the difference is about 4 degrees. But if you go to where there's no water, to the jungle and to the open grass areas in the west, the difference is up to 7 degrees. So, because that can also cool out faster in the night, So you have completely different, not completely, but much cooler, much more comfortable climate there. So if you would take away the buildings, you would reset back everything into nature. But of course we cannot do that. We have to understand how all these processes are working. And this is where a combination of cognitive computing, of knowledge from our part, of technical knowledge, of observations, of data, of information has to come together. And if you do that, maybe then we can start to understand what the real effects would be. For example, is the local climate zone in Singapore directly affected by this heat rising up from the streets? What many people think, because they cannot predict the weather in Singapore or in any other places which have a local climate zone anymore. And then you can already imagine how much interaction happens between these different factors in the urban climate. So whatever you do in your proposal, in the exercise, think of the side effects. Here, for example, in Singapore, if you would say, yes, we want to reduce industry, we take a different kind of industry. That probably wouldn't do any harm to the environment, and you wouldn't have to do any additional measures. It might do some damage intermediately to the economy. Could be, for a while. But Switzerland, with the same amount of input, also, and other countries too, get more output, because refineries are by definition a different kind of production. Maybe you switch the type of production. But even if you go to the cars, even if you go to the buildings that by themselves, through their roughness, have an impact on the heat island effect, maybe you would have to change the buildings by themselves. So you would come to completely different forms of buildings that have less roughness and which would be counterintuitive to many ideas that we have about cities and buildings in the tropics today. And from this you can go on and on and on, but I think in the end you will come to good conclusions or proposals. Let me finish up. In this course we went through the different developments of cities and buildings, from geometry-driven planning to sequential planning to functional planning to the urban science, if you remember that, to complexity science, informed design, to now the newest versions that we just showed you before, big data informed design. And they're connected. The urban science, the complexity, and big data are connected. They're connected through land use planning, generative design, the complexity science informed design through stocks and flows and quantum city observations, then the big data informed urban design through citizen design science and cognitive design computing. If this will take off, we don't know. But if it does, then you were here at the right place. If it doesn't, then you knew it was a direction that didn't happen. In the end, everything moves from positivism, when people believed urban science can solve everything, was not questioned, like your question from the designers in the beginning, to something which is called crowdsourcing today, which you all do for other purposes, and which have a much more questioning built in, but also a much more maybe intelligent result. So we come to the conclusion. The cognitive computing began a long time ago as a concept in the late 50s, and it was related to artificial intelligence. It still is. Architecture was a very good application area, but not too much research could be done because of the lack of funding and all other kinds of necessities. Urban design is an even better and more interesting application area for cognitive computing, because the amount of decisions to be derived from citizen input, transportation needs, and external requirements is much higher than in individual buildings, architecture. The cognitive design computing, we think, will be the combination of the above. From architectural design, it takes the abstraction methods that were developed over the centuries and the deep knowledge about materials, climates, and the human use of the habitat. So with that, I want to close. I want to invite you again next Monday from 2 to 6 here, and then the apéro at 6 o'clock on the next level down there. And I hope to see many of you, most of you, listening also what the others have done in the other courses. Thank you very much and have a nice afternoon.